We talk about particle representations and limit theorem for stochastic partial differential.
I doubt if anybody in the back of the room will have trouble hearing me, but am I being recorded, I guess would be the question. Let me find the various pieces of mechanical equipment that I need. What did I do with the... Okay. Now, the first thing I would want to point out is this line here about from particle approximation to particle representation. There's a huge literature on what would be called particle approximation. For example, I'm sure many of you are aware of the work that Denny Tilley and his group at INRI have been doing, where they've been using particle approximations to solve or approximate the solutions of nonlinear partial differential equations. Of course, in the filtering literature, there's a huge amount of literature on computation of optimal filters using particle methods. Last week in the network seminar, we saw Carl Graham talking about sort of limits of particle systems in networks. While there's a close connection between what people talk about when they talk about particle approximation, particle approximation, you have finitely many particles. What I mean by particle representation is what you get after the number of particles goes to infinity, but you keep the infinite collection of particles and try to see what knowing the infinite collection of particles lets you do about the limiting models that you're interested in. And again, in the networks literature, Francois Bocelli and David McDonald and co-workers have actually used some of these same ideas in analyzing, for example, a model of TCP. So, what are we going to do today? Well, the first thing I want to do is to talk about what is really a relatively simple model. It's a stochastic PDE that Peter Kotelenetz has loved for a long time. And I want to use some of the ideas, or illustrate some of the ideas, by actually proving a theorem about this particular stochastic partial differential equation. And after I actually try to indicate that one can actually prove something interesting using these ideas, I'll then give you a few more little twists and turns, other suggestions of where one might be able to use these kinds of representations. And finally, at the tail end, if there's any time left, which there never is, if there's any time left, say a little bit about another very similar kind of construction that Eliana Rodriguez and I have been looking at recently, and may be of use in the SPDE community as well. Finally, maybe I should also mention that this is one of those situations where one starts with something rather complicated and discovers that by making things simpler, you still find something which may actually be useful to somebody, because many of these ideas actually come out of some old work that I did with Peter Donnelly many years ago on finding ways of representing of constructing particle representations for superprocesses where you have branching. So in some respects, you can think about the models that I'm talking about today as branching models for which there is no branching. Okay. At any rate, here is Peter Kotelenetz's, or one of Peter Kotelenetz's favorite SPDEs. I'll motivate this a little bit later, but for the moment, let me just observe that if I take the test function, I'm going to write everything in weak form. Okay, maybe that's weak minds deal, I don't know. But at any rate, if I take phi to be identically 1, these terms, this has got a gradient of phi. This is a standard second order diffusion operator nonlinear because the coefficients depend upon v. At any rate, all this disappears, so if I take phi equal 1, we see that v epsilon of t is a constant, and in particular I'll simply assume that v epsilon, the constant, is 1, and v epsilon is going to be a measure, and so v epsilon is in fact a probability measure valued process. Okay? Now, let's get a little bit of Let's get a little bit of machinery to work with. The collections of particles that I'm going to be talking about will always be exchangeable. And if you don't know what that means, there's the definition. If I've got a sequence of random variables, regardless of what space they might live in, I say that sequence is exchangeable if permuting the indices does nothing to the joint distribution of the random variables. And then the classic result of De Finetti says if I have an exchangeable sequence, if I have an infinite sequence that's exchangeable, then you get essentially a law of large numbers. The only difference between exchangeable and independent is that the probability measure that goes in over here will in general be a random probability measure. In fact, exchangeability says that if you condition on knowing this random probability measure, then you get this identity, which says basically if I have an exchangeable sequence, then conditioned on the De Finetti measure, the sequence is IID. Okay? Now, this is a nice limit theorem, and it's a limit theorem that's very useful in a lot of contexts. But in the context of today's talk, think of the sequence, think of the exchangeable sequence as being a representation of the measure t. That's the sense in which I mean representation. I've got an exchangeable sequence that by an infinite exchangeable sequence by De Finetti's theorem, that determines a measure, okay? And my sequence is a representation of that measure. Now, I prove limit theorems for a living, and so here's a limit theorem on exchangeable sequences. So this gets a little bit complicated and tongue-twisting. If I have a sequence of exchangeable sequences, got it? Okay, n is going to go to infinity. This is a perhaps finite or possibly infinite, for each fixed little n, this is a finite or possibly infinite exchangeable sequence. The requirement here is that capital N sub little n is going to go to infinity. It may already be infinity. Either way, this is the empirical measure, or the infinite empirical measure. This is De Finetti's measure if capital N happens to be infinite. Otherwise, it's just the standard finite empirical measure. And the assumptions of the lemma are that capital N goes to infinity, and any finite subset of the random variables converges in distribution. And the conclusion of the theorem is that the limit has to be exchangeable. That's pretty trivial. But the interesting part of the theorem is you get joint convergence of the De Finetti or infinite or empirical measure. You get joint convergence of the measure and the sequence to the limiting measure and the sequence, where this capital C is indeed the De Finetti measure of the limit. Now, that doesn't look very hard. It isn't very hard. But let me just point out in passing, there is at least some content here, because if I replace the exchangeability assumption by stationarity, the lemma would no longer be true. You could not conclude that if this is an infinite sequence and Cn is the measure that would come out of the ergodic theorem for a stationary sequence, I could get convergence of this to this, but I wouldn't be able to automatically conclude that the capital C was the measure that comes out of the ergodicity for the limit. Okay, now we're really interested in processes, so there's a process version of this. If I'm looking at a sequence, if my x's are actually stochastic processes, say in some nice CAD-like space of right continuous functions with left-hand limits, if this family of processes now, again, it's exchangeable in the sense that I can permute the indices, I can talk about the empirical measure on this probability space, but I'm also interested in the empirical measure just on for the marginals, okay? And what this theorem says, or what this lemma says, is that if I get this nice convergence, then not only do I get convergence of, this is the previous result says that capital Cn goes to capital C, but I at least get the finite dimensional distributions of this sequence of processes converging. And you can see where this is, what's coming next is it's the V that's going to be the solution of the SPDE. And at least with a little bit of extra assumption, and since all of our processes are going to be continuous today, I won't give my usual lecture on the distinction between convergence in this space and the convergence in this space. They aren't the same, but in the case of C, they are. So once I know this for the continuous processes, and then in fact I can conclude that the empirical measure process converges as a process, as a probability measure valued process, okay? So, well, let's skip that. Let's use that. And here is where Kotelenitz's SPDE comes from. And this is a fairly standard sort of classical McKean-Vlasov kind of argument or a setup. Now I'm assuming I have a finite system. Capital N here is the number of particles involved. Each of these particles satisfies a certain SDE. This is a standard Gaussian white noise on some space U. I really don't care what U is yet. On some space U, so this is standard Gaussian white noise. This is just a diffusion process, and the dependence among the particles comes in two ways. One, they're all being driven by a common Gaussian white noise, and all these coefficients depend upon the empirical measure, okay? Now, the standard classic kind of McKean-Vlasov limit says, okay, you let capital N go to infinity, and you want to find a limiting equation that's an equation that's satisfied by the limit, okay? So what are we going to do? We're going to keep things simple today. So I'm going to assume that these coefficients are bounded. F is bounded in Rd, and this coefficient is bounded in the appropriate L2 sense. Okay, this is, I have to worry if this Gaussian white noise is determined by its covariance is determined by the measure nu, okay? Then I need this coefficient just to be bounded in L2 of nu, okay? So as soon as I have boundedness of these coefficients, proving the relative compactness, for in the sense of convergence and distribution, proving the relative compactness for xn is basically a triviality. Once I have if I have a process in a sequence space, once I've proved relative compactness for each component, I have relative compactness on the product space, all right? And then since all my processes are continuous, in this case, I'm going to have relative compactness in the space C, R, D, infinity, 0. In any case, I know I can pick out a convergent subsequence for the whole sequence of processes. By my previous lemma, that tells me that this V converges along with, if I pick out a convergent subsequence, then this empirical measure V converges along with the X's. I'm assuming continuity in these coefficients, and by this I mean continuity taking the weak topology on the probability space. And bingo, what comes out is that my infinite sequence in the limit, or my finite sequence in the limit as n goes to infinity, if I pick out a convergent subsequence, the infinite system that I get in the limit is going to satisfy this equation, where I know, because I started out with exchangeability, I know that whatever the limit is, this is, for each t, this is an exchangeable sequence, and this is, and for each s, this is an exchangeable sequence, and v epsilon is the Di-Finetti measure for this exchangeable sequence. Okay? So I get Kotelenitz's, and this, of course, is the way Kotelenitz's got it too. I get the Kotelenitz's equation. All right. What about a uniqueness for this kind of an infinite system? Well, there's one set of conditions which makes the uniqueness proof fairly easy, and that is if we assume these coefficients are Lipschitz, where we take this as essentially a Wasserstein-like metric. If I take this to be the metric on my probability measures, then if I have the Lipschitz condition in this metric, then existence and uniqueness for the system, for the infinite system that I've defined here, is reasonably straightforward. That, incidentally, just let me mention in passing, that kind of condition would imply uniqueness under all kinds of different assumptions about the driving noise. Prater and I have a result that says basically you could let the noise be indexed by I, and as long as your sequence of noises is exchangeable and the noises are in some, have some nice semi-martingale-like properties, then you would get existence and uniqueness for this infinite system. So this is a very general, this uniqueness in this setting is a very general result. Okay, now of course the problem of that is that this kind of Wasserstein-like Lipschitz condition is a pretty mild kind of nonlinearity, and so one would really like to be able to do a lot better than that in general. Okay, so here's my infinite system, all right? My suggestion was that this has something to do with SPDE. How do I figure out what the SPDE is? And again, everything gets written in weak form. Just take some nice smooth test function phi, apply Ito's formula to it. There's the elliptic operator that showed up on the first transparency. The xi's were exchangeable, so phi of xi is exchangeable, and when I average this, the average of this is just this, the average of this is just this. I can move the averaging inside, and this integral is going to go to this. I move the averaging inside, and you got to invoke some kind of a theorem about stochastic integrals, but the limit of the average of this is this. And so I end up with this identity holding for every nice test function phi, and that simply says that the V is the solution of the SPDE that I had down at the very beginning. Okay? And so this is exactly what I mean by a particle representation, and that is that the solution of this infinite system gives me, in this sense, a representation of the solution of this process. Okay? Now, I claimed that I could prove uniqueness for the infinite system, and in fact, it turns out that one can use the uniqueness for the infinite system to prove uniqueness for the SPDE by something that I'd call a Markov mapping argument. And if there's any time beyond the end, I'll say a little bit more about this, but for the moment I'm just going to say the idea is the following. I'm looking at a sequence of processes in RD. I'm mapping that sequence of processes into a probability measure value process. So I have a mapping that goes from here to here. I've got an SPDE with values in here, and what I claim is that this Markov mapping theorem lets me show that every solution of the SPDE comes from a solution of the infinite system of stochastic differential, ordinary stochastic differential equations. So if that's the case, then if I had two solutions down here, they would both map to solutions up here, but if the solution up here was unique, then the two solutions down here would have to be the same. That's the basic structure of the argument, and it works. Okay. Nobody asked, I expected somebody to wave a hand and say, what's epsilon? But maybe I talk too loud and too fast, so that sort of keeps things. So you have to learn to talk really loud and really fast. Nobody had such,
What's epsilon?
Oh, all right. Okay, so here comes epsilon, all right? Yeah?
But couldn't uniqueness fail because you have different ways of constructing an infinite exchangeable process that represents the same measure, so you could have different initial conditions for your...
Oh, you have to have the same, no, you have to argue you have to arrange things so they map to the same initial condition.
Yeah, but you have, for your SPDE, you just have an initial measure. So you only have the initial empirical measure.
That's right, so if I have an initial measure for my SPDE, that's a random probability measure, and the initial condition for my infinite system is conditioned on the initial distribution of the SPDE is just IID with that initial distribution. Okay? Okay, I have paused for breath, so if there's any more questions, I can, now's a good time.
Yeah, so are you saying the Markov mapping theorem follows from De Finetti's theorem, or you have...
No,
you haven't
I'm
explained
sure
it.
you've heard me talk about the Markov mapping theorem.
Well,
You forgot? No, the Markov mapping theorem is a general result in martingale problems, but yeah, it's just applicable here. Okay, so maybe we'll have some time at the end, or I can be happy to talk to anybody later. Okay, so what are we doing here? We're assuming that this is the diffusion coefficient. And what is this saying? We're saying that these j epsilons are a fixed j that's rescaled in a certain way. Okay, and if this fixed j is nice, square integrable, then when I do this rescaling, somehow the reach, let's remember the equation, if I, whoops, oh, I went the wrong direction. The reach of the white noise, or the effect of the white noise, is getting to be in this finer and finer area. Okay, I mean for example, if the J on the previous slide, for example, had compact support in U, as I scale epsilon, that support is shrinking to nothing, right? So the reach, the influence of the W is, that's the part of the W that's influencing this particle is becoming less and less likely to influence other particles. Okay, so that's what this zero correlation limit idea is going, or vanishing spatial noise correlation. Okay, so if I do this, if I assume that I have this kind of scaling, then under this assumption, you just do your change of variable, and it's not hard to see that as long as x1 is not equal to x2, as epsilon goes to 0, this integral goes to 0. Okay? And now what I'm going to assume is that that limit is in fact uniform as long as I keep x1 and x2 some distance apart and on compact sets in the measure. Okay? Then I need a non-degeneracy condition. This is just uniform ellipticity, basically, is what we're assuming here. And once we have that, the theorem is that as epsilon goes to 0, x epsilon converges in distribution to the solution of this SDE, where now I've got a WI rather than a W. And what this WI is, the WIs are independent. Okay, they're independent Gaussian white noises with the same Gaussian white noise as the original W. So the WIs are independent. And now if you look at this equation, play the same game, this equation satisfies you know, with the independence, when you do the averaging, with the independence of the WIs, they just average out, okay? And you end up with a standard-looking nonlinear PDE, and this is essentially the setup of the classical McKean-Vlasov equation, okay? So what we're saying is that as this correlation distance goes to 0, okay, the solution of the SPDE is converging to the solution of this nonlinear PDE, okay? So let's see how we might prove something like that. Again, well, yeah, let's pretend there was an epsilon on everything here for a moment. And remember, I'm assuming boundedness of the coefficients. So the compactness argument works just as it did when I passed from the finite particle collection to the infinite particle collection. It's easy to check that the xi epsilons are relatively compact. That gives you relative compactness for the infinite sequence. And the convergence lemma says any limit point has to satisfy this equation. Oh, well, wait a minute. I haven't told you what Wi comes from. And for any limit point, the v for the limit is the infinite empirical, is the De Finetti measure for the xi's. Now, what is Wi? Okay. Well, here's my equation. The print just got smaller. I hope you can still read that in the back. Here's my equation. It's got this funny rescaled coefficient. But if I do a change of variable in the stochastic integral, okay, call that Wi epsilon, then what Wi epsilon is you can check it. Wi epsilon is a Gaussian white noise. Okay, it's a Gaussian white noise and it satisfies this identity here. But of course, Wi epsilon, here sits the x epsilon. These Wi epsilons are not independent to start with. They're all linked back to this W, okay? But notice that, again, as epsilon goes to 0, suppose my phi has compact support. As epsilon goes to 0, then the reach of W that affects this term here is trapped inside an epsilon neighborhood of the path xi. And when I pass to the limit, remember we have relative compactness for the x epsilons. When I pass to the limit and I get some limiting xi, and I do the same thing and get some limiting xj, as long as the xi and the xj are separated by more than epsilon, okay, then the covariance of Wi epsilon and Wj epsilon is, this covariance is going to be 0, okay? And in general, as epsilon goes to 0, for any nice test function phi and any nice test function psi, this quadratic variation of this martingale with respect to the martingale corresponding to xj, that quadratic variation goes to 0. Okay, so I got a sequence of martingales. The quadratic variation of any one of them tells you that mi5 is for each, sounds like a spy story, doesn't it? mi5 is itself a Brownian motion. Its quadratic variation is a constant times t. And this has the covariation of two of these things is going to 0 at least as long as xi doesn't hit xj. Okay? Now, you may or may not have remembered way back in the beginning, there was an assumption that d was bigger than or equal to 2. Right? If d is equal to 1, then xi and xj will hit each other, and what you end up with is some kind of coalescing limit. Okay? But if xi and xj don't hit each other, then the limit of the Wi epsilons will be independent. Okay? And that will assure that the limit satisfies this equation with independent families Wi. Now, you may all believe, as I certainly did before I got involved in this project, okay, I've got processes here, x epsilon I and x epsilon j. They're diffusion-like. They're not exactly diffusions because there's this v epsilon floating around. They're diffusion-like, two-dimensional, and they're non-degenerate by the non-degeneracy assumption. Two-dimensional diffusions don't run into each other, right? I mean, I've known that, I think, since, well, not since grade school, but they don't, Well, you'd be surprised how difficult that is to actually prove, okay? 3 dimensions is not bad. 2 dimensions, you really need some additional regularity on this stuff to make it work, okay? So at least we needed additional regularity to make this work. Okay, so at any rate, we get the independence in exactly this way, and that gives us that gives us the solution of the infinite system, which gives us the solution of the McKean-Vlasov equation. And then finally, the thing that needs to observe, under the Lipschitz conditions we're operating on under J, the solution of this system is unique, okay? If the xi of zeros are independent, we've already said the wi's are independent. If I have uniqueness of this solution, then V has to be measurable with respect to the tail sigma algebra for the sequence that's generated by the initial condition and the wi. But if the initial condition and the wi's are independent, the tail sigma algebra is trivial. That tells me that V is really deterministic. And if V is deterministic and the xi of zeros are independent, then the xi's are independent. And that's the propagation of chaos result that goes with this. Okay? Questions? All right, so I hope I have at least teased you a little bit to indicate that, as I think, Francois and David started calling the keep the particle or bring back the particle method. Okay, the keeping the particles in the limit can actually be useful. You have this extra tool of this limit theorem. You have some extra flexibility when it comes to proving both existence and uniqueness. Okay, now, if you remember back on the opening slide, there was the beginning of this quote. If the only tool you have is a hammer, the rest of the quote, somebody? Every problem looks like a nail, okay? So if the only tool you have is a hammer, every problem looks like a nail. So, 2-3 weeks ago, Stella Brasesco was here, and she gave a very nice talk on a stochastically perturbed Allen-Kahn equation, okay? And I'm sitting back here someplace, and I look up, and I say, wow, a nail, okay? So, here's the hammer applied to this nail. I mean, I have no theorems that I proved here, but I'm now trying to tease you a little bit with some other possible examples for playing the game that I'm playing. What I'm going to look for is a signed measure valued process. We've been working with measure valued processes, but turns out, at least if you want to get something that looks sort of like that, you've got to be willing to work with signed measures. I want to look for a signed measure valued process, and I want it to have a density. I'm going to need the density of my signed measure valued process. And I'm going to construct it in the following way. If you dream about this sort of thing all night, then, it takes you, I don't know, it was only a half hour, but Dan Christen got involved and settled the fact that we, in fact, did have the right boundary conditions. But at any rate, so we start now with a collection, an infinite system, right? We're talking about infinite collections here, of independent reflecting Brownian motions on the interval AB. Okay, they're given to us. And we'll start them all with their uniform initial distribution. Now let's think what an infinite sequence of stationary reflecting Brownian motions, that's Lebesgue measure in my world, right? If I look at this infinite sequence, they're actually independent. What's their distribution? It's just uniform distribution on AB. So this is some complicated way of representing a Lebesgue measure. All right, then I need something else. I'm going to look at a family of processes AI that satisfy a stochastic differential equation that looks like this. G, incidentally, G in this case is just minus m squared minus 1. You know, that m gets used someplace else, but the G here is just minus m squared minus 1. And my A satisfies an equation that looks like this. Don't worry about these terms. You know, here comes, this is the Gaussian white noise, except I'm going to smooth things out. Stella was using, you know, white noise perturbation here. I'm going to regularize things a little bit, and we'll come back to that in a minute and see if we can do see what happens when we try to get rid of that. Okay, but all right, here's my A. And what these crazy terms do, it's much easier to explain it must be easier to explain the process than the equation. And that is, remember, I've got these Brownian particles, and they're reflecting Brownian motion on the interval A to B, or from your point of view, A to B. And when one of these particles hits the right endpoint, whatever the value of AI is, it immediately jumps to m plus, and when it gets back down to the left endpoint, it immediately jumps to m minus. Okay, so these particles, these AIs, they're diffusing around. This is, if W is Gaussian white noise, space-time Gaussian white noise governed by Lebesgue measure. This is just a Brownian motion. Okay, it's a Brownian motion. These are dependent Brownian motions because they depend upon xi and where the xi's are. But at any rate, this is just a Brownian motion. So the first part of this is just a diffusion process. The AIs are essentially Ornstein-Uhlenbeck-like models, except these two terms cause the behavior at the boundary that I described. Okay. So what's
the relation between I'm minus, I'm plus with A and B, and I'm minus, I'm plus between A and B?
Okay, I want the solution, when we finally see that what we're working with at least comes close to being the solution. I want M is going to be capital M bar, okay? And I want M to be equal to M plus at the right endpoint. I want M to be equal to M minus at the left endpoint. Okay, and I'm going to get that by forcing these stochastic AIs to jump to the right place when I get to an endpoint. Okay? Now, the capital M, the signed measure valued process, I get just by passing to this limit. Okay, I'm going to require the solution of this system to be exchangeable. I'm not claiming uniqueness here. Right? I have no idea. Okay, I'm not claiming uniqueness. I'm simply saying, but I can, I can construct a solution in a way that will be exchangeable. So if the solution is exchangeable, then this will exist. This limit will exist by De Finetti's measure, De Finetti's theorem. I claim that this is a nice signed measure with a Lebesgue density, and that comes from the fact that I know that the xi's, okay, are essentially a representation of Lebesgue measure, and to see that I'm getting absolute continuity here, just think of truncating these AIs outside of some big interval and seeing what the limit would be, and then recognizing that if I truncate the AIs, I get absolute continuity easily, and then I just let the truncation go to infinity. Okay, So this M will have a Lebesgue density, and that gets fed back in here, and so you've got to play games to actually show you get a solution here. Now, but it's a solution of what? Okay, there are a bunch of assumptions, and I think I've already said all of this, so I won't go through it again. Okay, so I want to derive the corresponding SPDE, okay? And that's going to be satisfied by this signed measure. And in order to do that, I'm going to explicitly model the xi's. Remember, the xi's are supposed to be reflecting Brownian motion on the interval 0, reflecting Brownian motion on the interval a to b. And this is the standard Skorohod equation for the reflecting Brownian motion. And if you're not familiar with that, you should have been here last week. In any case, I can write this stochastic equation where these are the local times on the boundary. And the BI's are independent standard Brownian motions. They're independent of everything else. Okay. So I play exactly the same game that I played in the Kotelenets case. I apply Ito's formula to this. I'll take my test function phi to have compact support inside the interval AB. Okay, that saves me from having to worry what those hideous boundary terms actually do here. So I get all this. I play the same game. I do the averaging. Out pops this. And as long as G is minus m bar squared minus 1, okay, then if this term wasn't here, what's left would just be the weak form of the Allen-Kahn equation, okay? With this term sitting here, what I have is the Allen-Kahn equation perturbed by Gaussian noise, but it's not white noise, okay? It's not white noise, because I'm doing this little bit of smoothing, okay? So, what happens then if I really wanted Stella's original equation, which had a white noise perturbation? What would I have to do? Well, I'd have to let epsilon go to 0, okay? So let's think about what would have to happen if I want to get white noise out of this by letting epsilon go to 0. Well, if I think of epsilon as being the diameter of the support of the rho is just some little mollifying thing. So I'm going to let epsilon be the diameter of the support of rho. I'm going to let epsilon go to 0. If I want white noise in the limit, then what I want rho to be, I want the integral of rho simply to be 1, say, some constant. Okay, so I want the integral of rho to be some constant. Okay, and that'll be fine if epsilon goes to 0, the support shrinks. I keep the integral constant. But then one might ask, if I do that, what happens here? Well, remember this term is just a Brownian motion, so letting epsilon go to 0 here is a lot like what we did in the Kotelenets model, with the Kotelenets model. So if I wanted this to turn out to be a bunch of independent Brownian motions, what would I have to assume about rho epsilon? Well, I'd have to assume that the integral of rho epsilon squared was constant, or converged to a constant. Those two conditions are not compatible. So either, if I want this term, if I want to keep this term, all of the Kotelenets result, and I have the integral of rho epsilon held constant, okay, then the integral, and I have the integral of rho epsilon squared held constant, then the integral of rho epsilon is going to go to 0, and this term is going to drop out, and I'm just going to get a, well, again, that's what happened in the Kotelenets case. I ended up with a deterministic equation, with the deterministic Allen-Kahn equation rather than the stochastic. On the other hand, if I hold the integral of rho epsilon constant, then this Brownian motion is getting a larger and larger variance, so this thing is going all over the place. Okay? That's fortunate if you think about it a minute, because there's nothing that I've done up to this point that's dependent upon the fact that I'm working in one dimension. I could do exactly this construction, say in a nice bounded region in 2 dimensions, where I've got my nice reflecting Brownian motions, normal, to keep things nice, normally reflecting Brownian motions that when they hit the boundary, the corresponding AIs jump to whatever boundary condition I want at that point. Okay? And of course, in 2 dimensions, this SPDE should not have a function-valued solution, right? And this is exactly why it doesn't. Or I mean, this is at least, allows for the possibility that it doesn't, because, whether I'm in any number of dimensions, this Brownian motion, if I keep the integral of rho epsilon constant, or whatever, well, that would be the right thing in higher dimensions as well. If I keep the integral of rho epsilon constant, okay, then this Brownian motion is going to go crazy. In 1 dimension, apparently, there's still enough averaging going on that you still get function-valued solutions, but it's the irregularity that exists in 2 dimensions, at least in this construction, that irregularity is going to come out of the fact that these are not well behaved as epsilon goes to 0. Okay? Now, here's your homework assignment. Due tomorrow afternoon at 5 o'clock. Okay? Find a part. I didn't think about this until this morning, but I think this will work. Okay? Find a particle construction of Professor Albavario's Fitzhugh-Nagumo model. Okay? All right. Moving right along. Let me see if I can tease you. Well, there's a slide with the stuff I just said about rho epsilon and rho epsilon squared. Okay. The interesting thing about this is I actually had it typed on the slide. I called this a fluid model. And I thought, okay, there are probably going to be some hangers-on from the networks where fluid model means something entirely different. This is real fluids now. Okay. So in any case, we'll go back to the original paper that I was looking at. No, this one here talks about a conditional McKean-Lagrangian model. And the model I'm writing down is really deterministic, although obviously you could tack on some more noise and make it stochastic. But what interested me when I discovered this is the boundary, again, the boundary conditions that showed up in the Allen-Kahn equation and how you match boundary conditions. That was sort of might be a useful idea in other places as well. But here is in the world of, Miro Bossi is the primary person, I think, in this effort at INRIA. And there you have a model in which there are boundary conditions. I've written it in my world of infinite systems. They do finite particle approximations, but I've gone to infinity here. So my xi is a location, ui now is a velocity. So xi is just the integral of its velocity, or that's where it started, plus the integral of its velocity. The velocity is diffusive. Here is a nice standard Brownian motion, in whatever set of dimensions you want to work. And here's the interesting, there are 2 interesting things in this equation, which I think place some challenges on the methodology, but in any case, I mentioned specifically the boundary condition. And what Ni does here, this is simpler than the Allen-Kahn boundary condition. the annoyance with the Allen-Kahn boundary condition is that your reflecting Brownian motion will hit the endpoint, infinitely often in a finite amount of time. So it's a bit of a nuisance. Here, you're only really going to hit the boundary finitely often in a finite amount of time. So Ni simply counts the number of times you hit the boundary and forces the velocity to jump according to this amount, okay? And it took me for a while to figure out, where did the 2 come from? And then finally I realized that their boundary condition, okay, first I need to tell you what this V is. Well, V is, in this my notation. V is my V. It's just the infinite empirical measure that goes with the pair xi ui, okay? But the thing that the nonlinearity that enters into their equation is the conditional distribution of u given the location x. Okay, so remember I've got infinitely many particles. I've got this nice finite region with, I've got infinitely many particles, which means in any little neighborhood I've got infinitely many particles. And so it makes sense to, sort of makes sense at least, to talk about the average velocity, at least in a little neighborhood. And since it's infinitely many particles, I can talk about the average velocity at a point, okay? So that's what this would turn out to be, okay? So again, they prove that, the thing I'm calling V here, in fact, has a density. So it makes sense to talk about the conditional average of the velocity at a point, okay? So the boundary condition then that this jump term is modeling, the boundary condition then is that the velocity at the boundary is the given external velocity, okay? So, I'm just throwing out teasers now, but that's, if anybody gets inspired to try to construct one of these things for something you're really interested in, there seem to be a variety of ways around of actually getting somewhere treating boundary conditions. Okay, my word, I have not run over yet. Anyway, that's a real rarity, incidentally. Okay. So one more. This is not another example. It's a different kind of construction. Okay. But one that is proving useful again in the superprocess world, which is where the motivation for this came from. But I think this also has some real potential in the SPDE world. In other words, you take your superprocess and you throw away the branching, and this is the sort of thing you get. UI is not a velocity now. I'm mixing, well, there are only so many letters in the alphabet. Okay, xi is a location, and we're going to keep things really simple. No nonlinearity. You can stick a nonlinearity in here if you want, but for the moment, we're just going to do linear. Xi is just a diffusion process, written in a slightly complicated way because the BI's are independent Brownian motions. The W is space-time Gaussian white noise again. Okay, so I've got two stochastic terms. This one is indexed by I. This one is common to all of my particles. Okay? Then I have something I'm going to call a level. Okay? UI is going to be positive. UI of 0 will be positive. Things are linear in UI. So UI is going to be positive. Okay, it's going to satisfy, this is just a linear equation once you have the solution for the xi. Okay, so once you know, say, uniqueness up here, uniqueness for the UI is trivial. Okay? And the game that we're going to play here has to do with the initial condition. Okay? And the assumption on the initial condition is that this collection of points in, well, these are positive. The UIs are always positive numbers. So this is, the UIs live in 0 infinity. The XIs live in any Euclidean space you would like to work in. You can do this in any Euclidean space. the initial condition for the xi ui's will be conditionally Poisson given, now this is a probability measure over the space in which x lives, and this is Lebesgue measure, okay? So by conditionally Poisson, I mean I condition, you know, a Poisson point process or a spatial Poisson random measure is determined by its mean measure, okay? So conditional on this, this is the mean measure for my collection of points, okay? Now what you discover once you, again, assuming you have uniqueness for the xi's, you automatically have uniqueness for the ui's. What you discover now as time evolves, at every time t, it's still the case that the collection of points, xi of t, ui of t, that collection of points, still form a conditionally Poisson random measure, conditionally Poisson point process, where the conditional measure, or I think we called it the Cox measure, because these things in statistics, these Poisson point processes with a random measure are called Cox models. So the Cox process that goes with this is some measure Vt dx cross Lebesgue measure, okay? Now, what does that buy me? Well, the first thing, before I see that it buys me anything, remember in the exchangeable case, we could use DeFinetti's theorem to say that if we were given an exchangeable sequence, we could recover DeFinetti's measure. It determined DeFinetti's measure. Well, we can play the same game with these conditionally Poisson things, because if I want to recover V of t, all I have to do is, you know, essentially look at all those points that are below all those points with levels below some level r, take this average, and let r go to infinity, and that's going to recover the V of t in my conditionally Poisson, in the Cox measure, okay? Now what's neat, you know, this is a nuisance. This is, I've got an indicator function here. But I can do it without indicator functions. I can, you know, put this little exponential in here, multiply by epsilon. I get exactly the same limit. Or I can do it with an epsilon squared and a u in there, or I can do it with an epsilon cubed. Okay? Now, why do I care about these last ones? Well, okay, I've got an infinite system here, and I'm claiming this infinite system is a representation for this V, okay, in the sense that I can recover V from the infinite system. Well, what the heck is V? Now, remember what we did in the exchangeable case. We just played games with Ito's formula. Well, if I tried to use if I tried to apply Ito's formula to this, I wouldn't get very far. But I can apply Ito's formula to this. And you do blah, 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 blah. You know, here I pick up a factor of u. Somewhere I pick up a factor of ui squared. Now I sum these things up. Remember, the ui of t's, my claim is that the uit's are really following the points of some Poisson process. So this, as long as phi is, you know, nice, this is nice and summable. I can sum this over I, multiply by epsilon, let epsilon go to 0, and then, you know, some places I've got an extra epsilon and a u, but I'm going to multiply by another epsilon, so I can apply this term, and then there's a one that's going to be an epsilon cubed, and I can apply this, and you chug all the way through, and lo and behold, out pops this very nice looking stochastic partial differential equation, okay? Now, one of the things that I like about this particular representation is, some of you may or may not be familiar with work that I did with Jay Shang, in which we use similar kinds of particle representations with what we call weighted particles, okay? The problem with weighted particles is that the measure that's involved does not come from a conditional distribution. However, in this representation, the measure does come from a conditional distribution. It comes from the Cox measure of the Poisson point process. So it turns out that if I know uniqueness for this system, I can play the same Markov mapping game to get uniqueness for this system. Okay? Now there's something else about this system that's nice. For the models that Jay and I looked at, the models always had to be measures that were finite. There's no reason whatsoever that v of 0 needs to be finite. I can play this game, say, with an initial condition that's just a Lebesgue measure on the whole space. All right? And this will work. Okay? So I can deal with this construction. We can generalize some of the uniqueness methods, and we can deal with measure-valued processes where the measures are in general infinite. And I'm only 2 minutes over by that clock, and I'm not over at all by this clock, so I'll quit.
Any question? So going back to the first part of the talk, so you have essentially two parameters, one epsilon and one n. Epsilon is a regularization parameter, n is the number of particles.
Yeah.
And if I understand well, if you fix the epsilon, you can make use of the definite measure to describe your limits. But do you have, is it what I didn't understand, if your definite measure is also a tool for checking the propagation of chaos, in fact, because at some point you did something like this, but
no, I mean the way actually that result came up is that this was a theorem that Peter was trying to prove. Okay, he was trying to prove that for the SPDE as epsilon goes to 0, he got some kind of limit, right? He wanted really the way he asked the question was, can you interchange the orders of the limits of epsilon and n, is the way the question was posed, okay? And with my hammer, my one tool, I said, that's got to be, okay. And so, the way the construction is used is really to apply the limit theorem, okay? Because we look at the infinite system, we look at the infinite system. Again, parts of this become very simple because the relative compactness, at least under the bounded assumption, is easy. So I know that I have limit points of this infinite system. I know that the v epsilon, the limit of the v epsilon, is the Di-Finetti measure for the limit. And then what I need to do then is to identify, I get the limiting equation, I need to identify the limiting equation and prove that the solution of the limiting equation is unique. And the way we identified the limiting equation was to rewrite the equation in terms of these W epsilons. Okay, so now I have the W epsilons. They aren't independent, but they are exchangeable. Okay, so I've got this system that's driven by exchangeable noise. Okay, I mean it's the same system, so nothing's changed really. So I let epsilon go to 0, and written this way, it becomes very easy to identify what the limiting the limits of the Wi epsilons are. And as soon as I verify, and that's where this hitting condition comes in, as soon as I verify that the limits of the Wi epsilon are independent Gaussian white noises, I'm done. Okay?
Another question?
Other questions? Yeah.
I have a naive question. I mean, you are basically constructing, let's say, a process which, in the end, locally is the mean field process associated with this. You could say that.
Yes, yes. With this very, you mean because these nonlinearities are very minor.
They're taken and just the,
Yeah,
just,
exactly.
just the mean field interaction. Now, of course, when I look at something like the Kahn-Allen also in equation, there are two points. I mean, they should represent the behavior of a particle system, where I should say, but the whole point is, of course, that the local measure is very far from mean field, right? It should be a Gibbs measure, and the local Gibbs measure should not be unique, which is the whole point of the two phases, right? Now, the question why I was puzzled and asked about this, I mean, when you want to apply finally anything that you know about the infinite process xi, is there kind of a condition which you did not talk about, that these xi's actually exploit the whole space, so that you are somehow in some way sure that boundary conditions for your PDE are felt by this limit?
Oh, well, in the Allen-Kahn construction,
Yeah, there I saw how you did it.
yeah, that's easy. The xi's are just given to you, and you know exactly what the xi's do.
This was a kind of general, right?
In general, well, you can recover, something about the local behavior. I mean, there is these, at least in the nice cases, you can. I mean, while these V's are sort of global measures, well, certainly in the case that I was talking about from with Kotelenets, and in these more general models that Jay Strong and I looked at, the models do have densities, and these densities are determined by the local behavior of the process. So there is buried in there is some local behavior. Now, I'd be very happy to see the example that you have in mind and see if there's anything that it might say about it. Okay. And I should point out that there's no particular reason. All the extra components, the xi's and the ai's, were all diffusive here, but there's really no reason that I couldn't do something very similar to the Allen-Kahn equation using ai's that are discrete. And that might get closer to something that you would be interested in. Okay. Francois?
Yeah, in some of the very specific examples we looked at, and so sometimes it was quite difficult to get the tail behavior of the distributions from the PDEs. And
Say, I can't quite hear.
To get the tail distribution of the solution of the PDEs, or the speed of convergence of this type, that was easy through the particle representation. So my question is whether it's possible you have the same phenomenon here, and generally speaking, can you analyze the tail behavior of the solution of the PDEs from the particle representation?
Well, certainly you can in some situations. We do that a lot in the super process models. There are lots of things. We haven't. I haven't done that so much with the SPDEs, but there are lots of results using these similar kinds of constructions in the super process setting. There are lots of conditions. Going back to your question, now that I'm looking behind you and thinking, in your model of the TCP behavior, the sort of averaging that gets done really is over discrete sets, right? And so there really is, there's local information built into their model of TCP behavior, which is, even though in some sense these measures are, you prove their existence kind of globally, and they enter the equation in a kind of smooth way. there is some information about the local averaging in the model as well.
Okay, let's thank the speaker.